Video is on Chapter 19, Electrophilic Aromatic Substitution Reactions, Activity 1. Okay, so we are going to be looking at electrophilic aromatic substitution reactions, and they proceed by this general mechanism where the aromatic ring acts as a nucleophile. It's actually a weak nucleophile, but it's good enough in this reaction because the electrophiles we'll be using are very strong electrophiles. So not being specific, looking generically right now, the aromatic ring attacks the electrophile, and if there's a leaving group, it leaves, and then we get this non-aromatic compound. So temporarily, you lose aromaticity, so this is a high energy intermediate starting material. It has a name, it's called the uranium ion, also sometimes called the sigma complex. Resonance stabilized, so even though it's not aromatic, it still has some stability through resonance stabilization. And it will quickly lose a proton at the same carbon where the electrophile added in order to regenerate a pi bond and regenerate the aromatic ring. So overall, it's an energetically favorable reaction because it starts aromatic and ends aromatic, even though the intermediate is not aromatic. Let's look at some specific types of electrophilic aromatic substitutions. The first one we're going to look at is the Friedel-Crafts acylation or alkylation reaction, excuse me. And we're going to be drawing in lone pairs and arrows, curved arrows, and also labeling the steps according to Klein's method of labeling methodistic steps. Okay, so we are going to add in some lone pairs on the halogens. Remember, aluminum doesn't have any because it's an exception to the octet rule. So it's only making 3 bonds. It only has 6 electrons around it. But even though it's an exception, it's still highly electrophilic. One of the lone pairs can do a nucleophilic attack on the aluminum. By the way, this is also called a Lewis acid-base reaction because Lewis defines an acid as an electron pair acceptor and a base as an electron pair donor. Even though there's no proton transfer, this is still a type of acid-base reaction if you utilize Lewis's definitions of an acid-base. And then this is sometimes called the Lewis acid-base complex. Okay, so I'll sometimes refer to these as the Lewis acid. I want you to be familiar with what I'm talking about here. Okay, so that's the first step. We form this complex. Notice now aluminum has a negative charge, chlorine has a positive charge. Chlorine only has 2 lone pairs now, and all the other chlorines still have 3. Okay, at this point on the activity, they do loss of a leaving group to form a primary carbocation. But I'm not going to do that, okay, because I always teach my students no primary carbocations. They are too unstable to form. Okay, so we are not going to do that. Instead, we can go directly from here to here in one step and avoid forming a primary carbocation. And the way we would do that is to show loss of a leaving group, right? And if I just did that, I would get to this intermediate. But at the same time, I can have the nucleophile attack. And the nucleophile, again, is the aromatic ring. It's one of the pi bonds of the aromatic ring axis. And with benzene, it wouldn't matter which pi bond you chose because they're all okay, so in this case now, I'm just combining those 2 steps and I'm going to label it another nucleophilic attack plus loss of a leaving group. Let's look at that leaving group. The leaving group And you would think, okay, why didn't chlorine just up in the leading group? It is, but this is an even better leading group, right? So it really activates it for nucleophilic attack. The reason why we need a super great, awesome leading group and not just chloride is because our nucleophile is terrible. It's a very weak nucleophile. And normally you know that weak nucleophiles don't do SN2 reactions. And that's essentially what this step is, an SN2 reaction. Right? So nucleophilic attack also. So with poor nucleophiles, typically we don't do SN2. But what counterbalances the fact that we have a poor nucleophiles, we have this fantastic leading group, chlorine having a positive charge. Okay, so you can see that it has left, right? And we've done our nucleophilic attack all in one step to prevent formation of a primary carbocation. So this is that rhenium ion we were talking about earlier. Right? We've temporarily lost aromaticity and formed a resonance stabilized carbocation. Okay, so from here, we can do a very fast proton transfer. And sometimes people just draw it from chloride because chloride can disassociate with this aluminum complex. Or you can just draw it directly from the leaving group. You start on the bond, pick up the proton here, and then show the formation of the double bond. Regenerate the aromatic ring. Okay, so basically what we did here, we did the two necessary steps, the nucleophilic attack, formation of the rhenium ion, and the proton transfer. The first step was just because the two reagents needed to react together first so that we could get a very good electrophile for the reaction. The next reaction we're going to talk about is the Friedel-Crafts acylation reaction. So the last reaction was an alkylation, and this one is an acylation. Right? So when we do an alkylation, we introduce an alkyl group on the aromatic ring. When we do an acylation, we introduce this, what we call this acyl group. It's a group where there's a carbonyl immediately attached, followed by any R group. So similar, but not exactly the same thing. The Friedel-Crafts acylation starts out with what people call an acyl chloride, or sometimes called an acid chloride. But you can see the similarities. We're still using the aluminum chloride Lewis acid. One of the lone pairs on the chlorine of the acyl chloride will still do a nucleophilic attack in a Lewis acid base reaction to form the complex. So we add in our lone pairs. That was requested. Technically, all these chlorine lone pairs are not necessary, but I like to add them just to be super clear. Okay, at this point, remember we did not show loss of a leading group to form primary carbocation. That's unreasonable. Secondary or tertiary would be okay, but not primary. But in this particular case, we can do it. Okay, and the reason why is we're forming a much more stable carbocation. So this is more stable because it's resonance stabilized. Notice here the resonance arrow. Sometimes people will even put brackets around resonance structures to really point out that this isn't a mechanistic step, it's just drawing two resonance contributors. So because it's a resonance stabilized carbocation, it's much more stable than a primary carbocation. This actually has a name. This carbocation is called an acylium ion. You know, sometimes certain things have names, like you've heard of hydronium ion, things like that. So when they have a special name, I like to point it out. Okay, so we are we are going to move on. Okay, so we have formed our acylium ion, and we lost this as a leaving group. And we are going to show the nucleophilic attack. Right, so the aromatic ring will attack the carbon. If you have a triple bond, you need to send those lone pairs up to the oxygen to avoid exceeding the octet rule. Okay, so this is a nucleophilic attack. And that gets us down here to the uranium ion, which is a common intermediate in all of these electrophilic aromatic substitutions. Now we need a base. Remember, we can just get a chloride from the leaving group, come in and act as a base to regenerate the aromatic ring. Okay, so that is a Friedel-Crafts acylation, and they're very similar, but not exactly the same as Friedel-Crafts alkylation. Okay, so it wanted you to evaluate the mechanism of the Friedel-Crafts alkylation acylation. What are the differences between the two cationic species A and B? Which will undergo a carbocation rearrangement and which cannot? So we drew he drew a primary carbocation, which in reality never forms. We'll just draw it just for comparison. Right? And compared to the acylium ion, which was a mixture of resonance contributors. This was A, okay, and this is B. So we know that regular carbocations can be rearranged. Right? So for example, we could, I'm just going to switch this maybe to a different carbocation because it just really bothers me. And then this can't form, so I hate to draw something like that. But let's say we had generated a secondary carbocation. We could technically do a rearrangement. For example, you could do what's known as a hydride shift. Okay? And that would basically, this hydrogen and the electrons shift over. That goes from secondary to a tertiary carbocation. So acylium ions do not rearrange. Okay? No rearrangement is possible here. That's something that's good to know. Okay, let's keep moving on, and we're going to draw a mechanism for following electrophilic aromatic substitution. Right, so this is another Friedel-Crafts alkylation reaction, but it looks like a rearrangement has occurred because of the way that it's not a propyl group attached, and so it's an isopropyl. Let's look at how that can occur. So we'll start with our alkyl halide. Just like we showed before, it can interact with aluminum acid. Instead of aluminum, we have iron, but it works the same way. And so one of the lone pairs on the bromine can do a nucleophilic attack. And sometimes people just shorten this just because it's a little bit faster. Don't forget the charges of this. Okay, so that's our Lewis acid base complex. And you might think, okay, I'm just going to lose this leaving group. The problem is that would generate a primary carbocation. Just have loss of a leaving group here, and the carbocation goes on the primary carbon. That's not good. So what we can do to avoid ever having to generate a primary carbocation is do a simultaneous hydride shift. The hydride shift occurs at the same time as the loss of a lead. That will immediately get us to a much more stable and more reasonable secondary carbocation. Plus, have the leaving. And at this point, this is a good enough electrophile for the aromatic ring to come in and do its nucleophile attack. Remember, we need a pretty strong electrophile in order for the weak nucleophile to get involved in the reaction. So now the aromatic ring can do its nucleophilic attack. That will generate the erenium ion. Which is this. So it's resonance stabilized, but we just don't need to draw all the resonance contributors. And then this can come in and act as a base and generate the aromatic ring. Now notice how we have a substituted benzene, isopropyl benzene. Okay. Next we have a bromination. So now instead of adding an alkyl or an acyl group, we're adding a bromine. But you're going to notice the mechanism is pretty similar. So bromine, if we draw it out like this, Br2, and if we treat it with a Lewis acid, it can react together in the same sort of acid-base reaction we've been seeing. Lewis acid-base reaction. And so the nucleophilic attack forms a complex. That helps because bromine by itself, while electrophilic, is not very electrophilic. So this actually helps form a much more electrophilic form of bromine. And from here, we can show our aromatic ring doing its nucleophilic attack. Lewis acid basically just makes bromine a better electrophile, which is important because we're using a really weak nucleophile. So we can do our nucleophilic attack. Interestingly, the aromatic ring will attack this bromine, and then this one will act as the lead. So oftentimes things attack the atom attached to the atom with a positive charge, instead of directly attacking the atom with a positive charge. So this gets us to the erenium ion. And at this point, I draw in this hydrogen attached to the same carbon as where the bromine got attached, because we need to show the proton transfer. So at this point, even though it's not drawn in initially, draw it in eventually. And then the leading group actually acts as the base. So you can go ahead and draw that in, then show it doing this. So really the bromination is very similar to the Friedel-Crafts reaction that we just did. Now we have a halogenated. And this would work with both bromine or chlorine to form bromobenzene or chlorobenzene. Okay, so this activity is all about drawing mechanisms. Okay, so we're just going to keep going with our mechanism drawing. So the next reaction we're going to be looking at is the Friedel-Crafts electrophilic aromatic substitution called a nitration. All right, it's not a Friedel-Crafts reaction. Why I said that? It's just a nitration. And in order to get a nitro group onto the ring, we need nitric acid and sulfuric acid. So both very strong acids. Sulfuric acid is a bit stronger than nitric acid, but this would be a very dangerous reaction because of having to use some very concentrated strong acid. Okay, so let's look at how do we generate the active electrophile, because nitric acid is not a strong enough electrophile to react directly with the aromatic ring. So nitric acid, like this. That's the Lewis structure of nitric acid. You probably drew it in general chemistry back in the day. It's interesting because it has these positive and negative charges right next to each other. This is sometimes called a Zwitter ion. And even though it looks unstable, having them next to one another like this is actually more stable than just by itself. So you can kind of imagine as if the charges don't exist, if they're really stable. And for that reason, this oxygen is not nucleophilic. It's actually helping to stabilize the positive charge. It looks nucleophilic, but it's not. This oxygen is actually more nucleophilic. And so if I draw out sulfuric acid, as I mentioned, is a stronger acid than nitric acid. We can donate a proton to nitric acid. And this oxygen actually is the one that takes the proton. So that, we draw out the product of that proton transfer. All those lone pairs. It looks like, oh, this is so weird, two positives next to one another. But remember, this is almost like canceled out. So don't worry about it. So we recognize that we have a good leaving group here. So we can leave. We can show water leaving. And at the same time, we can actually show our resonance here. That will get us to one of the resonance contributors, and usually the one that people draw most often. This is the active electrophile. This is what gets attacked by the aromatic ring. It has a special name. Remember the acylium ion that had a special name? This is called the nitronium ion. Sometimes names can help us remember what's important in the mechanism. It's good to think about names. Okay, at this point, once we've generated the active electrophile, we can get the aromatic ring involved in doing the. Remember, you can't exceed an octet on nitrogen. It's a second row element like carbon. So we have to draw this resonance arrow at the same time as the nucleophilic. That means we will now have our uranium ion. If I draw out the nitro, you can see what it looks like. Oftentimes it's abbreviated. It's just NO2, but this is what it looks like drawn out. So it's good to know what the abbreviation means. Okay, and then the last step is the proton transfer. In this case, we didn't use a Lewis acid, so we're not using the same sort of base. You can actually just use water as a base. This will have some water in it, acids. So water will act as the base to do the final proton transfer. Then instead of drawing it out, this time I'll just. Okay, so now we're able to introduce an alkyl group, an acyl group, a halogen, either bromine or chlorine, and then nitro. And the last electrophilic aromatic substitution reaction is the sulfonation. The sulfonation, in and of itself, is not very interesting because notice there's not a whole lot we can do with the sulfonyl group synthetically. However, why this is included and it is interesting is because this reaction is actually reversible. The fact that we can use concentrated acid to put it on, dilute acid to take it off, that will actually become advantageous for us synthetically. So that's why this reaction is introduced. Is important. More about the fact that we can use it as a blocking group later. We'll see how to do that and then remove it like it was never there. Okay, so the good news with this one is we don't have to generate the active electrophile. It is already there. So concentrated sulfuric acid is sometimes known as fuming sulfuric acid, because if you open up a bottle, fumes immediately come out, noxious fumes. And the fumes are actually the electrophile. What are in the fumes, right? So what it is sulfur trioxide, which is present in super concentrated solutions of sulfuric acid. And it's volatile, so that's why it's present in the fumes. Sulfur is highly electrophilic, which is great because we have a poor nucleophile in the aromatic ring. Notice that I did draw sulfur with 6 bonds. That's okay because sulfur can exceed an octet and expand its octet. Don't worry about that. So we have our nucleophilic attack. That's going to generate an uranium ion. And then what we have is drawn out, and later I'll not draw it out. That's what this would look like initially after the nucleophilic attack. And then, because it's this acid solution, there's definitely some water there. So we'll do a fast proton transfer. So now I have the SO3 minus, and it's in a very concentrated acid solution. So it will just pick up a proton, plus a proton from sulfuric acid most likely, and become neutral isolatable product. Okay, so now we're challenged to draw a reaction we've actually seen before, but this one is a little different in that it's going to be intramolecular. So notice in the reactant we have both the aromatic ring and an acyl chloride. We're treating that with a Lewis acid. So this is the Friedel-Crafts acylation reaction. The mechanism, right, it might seem different because it's an intramolecular reaction, but it's not really. Okay, so the first step is, remember, the lone pair on the chlorine attacks the electrophilic aluminum on the complex. That makes an even better electrophile. So now we have generated the Lewis acid-base complex. In this particular case, typically people show the loss of a leaving group to form the acylium ion. And the carbon on the acylium ion is sp, this carbon right here, sp hybridized. So we typically draw that linear. And then we also have picked out leaving group. So now this is a very, very electrophilic carbon, and we have the aromatic ring, which can do an attack. Notice that we either need to show this carbon or this carbon doing the nuclear, because the acyl group ends up next to the alpha group. So, and it doesn't matter if you show this one or this one, they're equivalent. You just want to start from the pi bond associated with that carbon. So if I was going to show it at this carbon, I would use this pi bond. If I wanted to do this carbon doing this, so I'll use this one. It's convenient for me. And now we have a sodium ion. Draw that hydrogen in so that we can do the proton transfer. There's that final proton transfer. That regenerated our aromatic ring. Product. This was just an intramolecular Friedel-Crafts acylation reaction. Okay, now we are going to start drawing more of the same mechanisms we've been drawing. The difference is that we're starting with a substituted benzene. So previously we've always just used benzene. We can still add a nitro group or any of the other groups and adding to a ring, even if it already has one or more substituents. A big part of the next activity is going to be figuring out where does it go. Okay, where does the nitro go, or the incoming electrophile, where does it go on the ring? Because if you put it here versus here versus here, they're all different products. So we're not going to be worried about predicting which product is formed. We're just going to be generating the product shown. That may or may not be the major product. In fact, in this section, this is a very minor product. So it's not even the major product. But remember, with the mechanism, that's not important. The mechanism is explain how this is possibly formed. It doesn't necessarily mean product. So we're not going to be worried about that. We're just going to generate this through the same sort of mechanistic steps we've been showing. And then later on, we'll figure out how to know where does the nitro go. And it doesn't go here primarily, in fact. Okay, so remember that a lot of times we have to generate the active electrophile. And a nitration is one of those cases, right? We have to show the nitric acid reacting with sulfuric acid, losing water to form the nitronium ion. So the generation of this electrophile was shown previously in the video, so I'm not going to show that. But we'll just start with the aromatic ring reacting with the active electrophile. In this case, we need to be very careful which pi bond here we use to do the attack, because this is no longer benzene. All of these pi bonds are not equivalent, and because it's substituted, right? So we want to show the pi bond associated with the carbon where the group ends up. So the best thing to do is figure out where is that carbon, the nitro is going to go, where is the pi bond associated with that, and use that particular pi bond. So we're going to put the nitrogen here, positive here, and then show the proton transfer. Right, remember, this one has water in it, so we just draw water as the base. Now we have generated the product that the mechanism asked us to generate, which is actually a very minor product in this reaction. We'll find out more about that next time. Byproduct of this last acid-base step is H3O. Okay, next one is another bromination. And again, the bromine reacts with the Lewis acid to generate active electrophile. So drawing out that complex, we've seen how to generate that before. Missed it, go back in the video. First we generate the Lewis acid base complex and then the aromatic ring and bromine. And note how I'm figuring out where my bromine got attached. I want to use this to do the nucleophilic bromine complex. That way I can place the bromine at the carbon that I want. Okay, I'll draw in that hydrogen because you know I'm getting ready to do the proton transfer. So I'm going to generate the leaving group. In order to show proton transfer. And get to the product. Okay, next one is a fruit-cross alkylation reaction with rearrangement. Notice how the bromine is attached here, right? But we're introducing this tert-butyl group, and it's, this tertiary carbon is what gets attached, not this. We're going to have to do a rearrangement. So to show that, we can start with our alkyl halide, draw out the Lewis acid, and show the Lewis acid base reaction to form the complex. Remember, that makes the bromine attached to the carbon positively charged. So that's very, very electrophilic and really a very great leaving group. So if I was just to show loss of a leaving group, what sort of carbocation would I get? I would end up with the carbocation here. That's no good, I can't draw that. So I can do a simultaneous hydride shift. That way I can draw much more stable tertiary carbocation, which is fantastic. And we can also draw out the leaving group. So we know we'll need that for the final proton transfer. Right, once we have the carbocation, tertiary carbocation, that's a strong enough electrophile for our aromatic ring to get involved. Note that I'm using isopropylbenzene. And I want my tert-butyl group to be attached to this carbon. That's where it's attached in the product. So I'm going to use this pi bond. And again, we'll learn how to predict which pi bond to use next time. Okay, so now we have the uranium ion, like this. We can do our final proton transfer. Product. An isopropyl and a tert. By the way, one of these mechanisms will definitely be on it. I'm not spending this much time working on them without putting it on the quiz. Okay, a sulfonation. Right, this one we get a little bit easier because if we just remember, we don't have to generate the active electrophile. We can just draw it. Right, so it's that sulfur trioxide. And again, we know our sulfonyl group ends up here, that carbon. So I'm going to use this and then draw a resonance arrow as well. That's going to put on S. There's some water that can act as the base in this reaction. Go ahead and draw that in for the final transfer. Generate the aromatic ring. However, our organic substrate here is still charged. So we still need to pick up a final proton from sulfuric acid to generate the neutral sulfonyl group. And generated from hydrogen. Byproduct. Okay, next one is a Friedel-Crafts acylation reaction. So we have this acyl chloride here, which we know gets activated by attacking the Lewis acid. Now we have complex, just like phenyl, eating this group as pH. Add in some lone pairs, charges. So that's our Lewis acid base complex. We know that that breaks down the loss of the leaving group to form psyllium ion. Which is the active electrophile. Now I can show my aromatic ring doing its nucleophilic attack. Note where the acyl group needs to end up, that carbon. So we're going to go ahead and use this even nucleophilic attack. Oops, I wasn't supposed to draw that. Instead, there's a positive charge here, hydrogen, which we need to deprotonate. So in this case, our Lewis acid is the base, chloride formant. Right, next is another intramolecular Friedel-Crafts acylation reaction. So initially, we form our acid-base complex. So by the time you get done drawing all of these out, you should hopefully be pretty good at drawing. There's our complex, and we can go ahead and pick out the leaving group to generate the psyllium ion. Shouldn't have bent that, but too late to change it. Okay, so there's the acylium ion, and then looks like I want to attack with that carbon. So then I'm going to use this pi bond. Almost done. We just need to draw the final proton transfer. So the kicked out leaving group will chloride attached to that will be the base. Product. The last part of this activity is a review activity. Make sure you keep up your skills on the Diels-Alder reaction and some other things. So it looks like this is our diene and dienophile. Right? The electron donating groups are only alpha groups. So there is no delta negative here. This might seem a little bit different than the key, and that's because I disagree. Right, so we're not going to get any major regioisomers. We're going to end up having to do both. So if they attack in this general orientation, then we would end up with the and end up with this product. I didn't draw this on a dash or a wedge because it's not a chiral center. The ketone approaches endo, so it ends up down on the bottom approach. You also get the enantiomer. But it's possible that the dienophile is flipped over and the approach is different. So in that case, we would end up with the bottom carbon. In this case, we would really end up probably with a mixture. Because again, these alkyl groups don't donate through resonance. So there's no particular delta negative here. They're both equal. And as a result of them both being equal, they both might be aligned with the bottom carbon, leading to a mixture, which is not ideal. For the next one, it's the same thing, right? The electron donating group is an alkyl group, which means there's no selectivity. Even though this one has the delta positive on the dienophile, it doesn't matter, we're going to end up with a mixture. So we just draw what that would look like. In this case, because it's cyclopentadiene, we're going to end up with a bicyclic product. I typically like to draw that like this. Add an alkene. Here there's going to be an isopropyl. And then if it approached from this relative orientation, the nitro group would end up on this carbon. Since it would prefer endo, it will end up like this. This has chiral center, so of course it's possible that the opposite relative orientation happened, and if that's the case, then the nitro group would end up on the other carbon, leading to a totally different product, but also quite possible to form. You really end up with a mixture. Okay, Grignard, 3 different Grignard reactions. So that kind of depends on which bond you're making. So this first one would be making this carbon-carbon bond, in which case the side with the alcohol was the ketone, and then the side that doesn't have the alcohol was the Grignard reagent. It's also possible you made, for example, this bond. And if that's the case, then you have a new ketone and a new ingredient. Could have also made this bond with a methyl. Right? And if that's the case, then we have the phenyl and the cyclopentyl attached to the carbonyls, this particular, and a methyl bringer. So it's about recognizing when you have an alcohol attached to a carbon, any of those carbon-carbon bonds directly adjacent could have been made through. And all of these, of course, would provide the proton on the alcohol. Okay, lastly, we're looking at epoxides in chapter 14. And we have treatment with LAH followed by an acidic workup. So LAH is a strong nucleophile, no acid present. It will attack the less substituted side. After the acidic workup, you would end up with just a methyl and an OH of this carbon, and hydrogen gets added here, which we don't need to draw. And this is no longer a chiral center, so I didn't draw any dashes or wedges. The next one is HBr. So HBr contains acidic protons and bromine. This is under acidic conditions. Under acidic conditions, the epoxide gets protonated, which makes this carbon-oxygen bond very weak. So the bromine will preferentially attack that tertiary carbon, more substitute. And the leaving group leaves from that carbon. So now we're going to draw the product, and we want to pay attention to stereochemistry. So end up with this. We want to show the bromine attacking from the back, and then you keep the groups on the dash of the branch. So that has the correct stereochemistry. Okay, stop sharing.